All right, hey everybody, welcome to video 13. Video 13, the focus here is going to be on angle, sum, and difference identities. So we're going to start looking at some more formulas and some more specific pieces and kind of adding to our formula sheet as we go. So you'll see me kind of add these in. Now the goal for this video and the goal for this lesson is to essentially look at how do we simplify and evaluate if I am going to add angles together, thus kind of the idea of angle sum. Or if I was to go through and subtract these angles, how do I go through and evaluate something like this? And then the following question, which I think is a really important one to kind of follow, to ask, is like, okay, well, why is this relevant? Like, why do I need to know how to do a plus b or a minus b and find the sign of that? And to go ahead and kind of precursor this question now and kind of spoiler this a little bit in terms of relevancy, is this gives me different forms of simplification. This form will also kind of lead to some other identities that are going to be very, very important, especially as you move on into calculus. And so I'll kind of point those out. That'll actually come into the next video. And so that's why it's kind of relevant. The other relevance is that although we're going to be adding angles, it always kind of goes back to the unit circle. And it kind of gives us a way to find some other angles that aren't on there, but we can find exact values for without using a calculator. So it kind of broadens what we can use the unit circle for. And so that's kind of answering the question in terms of relevancy. And so to start, I'm going to kind of break down the identities and we're going to look at them individually. So what if we just did angle sum? And so what you'll see is, so finding a trigonometric function of the sum of two angles, where I'm going to call those two angles A and B. And so essentially what we're doing is saying, I want to know what is sine of these two angles being added together, what is cosine of these two angles being added together, and what is tangent of these two angles being added together. And according to the identity and the process and the proof behind it, sine of A plus B, it actually turns out that this is going to be equal to sine of A cosine of B plus cosine of A sine of B. In other words, you would think that this would be just the sine of A plus the sine of B, but it turns out that it's a little bit more than that. It actually involves cosines as well. And so this isn't directly equivalent. And so sine does not distribute like multiplication would if it was 3 on the outside of parentheses. And so that's probably the most important thing to kind of take away when we're looking at these formulas. Now, cosine of A plus B actually looks a little bit different than sine. It's cosine of A, cosine of B, minus sine of A, and then sine of B. All right, and so this is the format for cosine. Now, one of the ways that I help to just try to memorize between sine and cosine, first off, is that the sine, so if I'm adding here, stays the same for sine. For cosine, it changes, so it's kind of like an S, same, C, changes kind of idea. Sine involves using both sine and cosine, and they're mixed up. Versus cosine, it's always cosines together and then sines together on the back end. And then tangent, which is kind of an oddball, it turns out to be tangent of A plus tangent of B. Let's try to make that parenthesis better. And this is all divided by 1 minus tangent of A times tangent of B. And so it's a little bit more complex. Now, you may be asking, okay, well, where do these formulas come from? Well, the good news is if you are interested in something like that, then that is actually one of the projects, is to go through, as you'll see right here, and actually derive these formulas. And you'll go through and actually create for sine of A plus B this equation, this identity. You'll do the same thing for cosine, and you'll do the same thing for tangent. And then it'll also lead you into doing the angle difference. Now, I'm not just going to leave this out and just say, okay, well, just go do it. There is going to be guidelines and a procedure that you can kind of follow, but it is still fairly difficult. So if you would like to do this project, I will count it as an assessment for angle, sum, and difference identities for those trig formulas. So just kind of know that. So if you're interested in doing that, attempt that. The due date is essentially the end of the mod, but I would try and get it done as soon as possible while the material is relevant and while the material is fresh. I'll be here to help answer questions, but I won't tell you how to do it. I will try to help push you in the right direction if you need it, like normal. All right, so these are the formulas, but let's go through and actually use them now. So this first example is specifically just going to be focusing on angle sum. So all of these can be solved using those formulas from up above. And so the first problem that we're going to look at, find the exact value for the trigonometric expression sine of 5 pi over 12. And because this problem is telling me to do the exact value, I don't want to use a calculator because a calculator is going to give me a decimal. It also is telling me that I can use the unit circle to help me do this one. But the problem is that if I was to go to a copy of the unit circle, I'm not going to see anything over 12, right? We only see over 6, over 4, over 3, over 2, or whole number pi's. So I need a way to find this though. And what I'm going to do is try to break this down into two angles that are being added together that are taken from the circle. So that means I need to look at pi over 6, I need to look at pi over 4, and I need to look at pi over 3, and let's rewrite these in terms of the same denominator, which is 12. So in other words, pi over 6 is the same thing as 2 pi over 12. Pi over 4 is the same thing as 3 pi over 12. And pi over 3 is the same thing as 4 pi over 12. So I'm just going through and changing to get the denominators, and whatever I do on the bottom, I do to the top. So I'm getting some equivalency here. And one thing that you may have noticed as I've gone through and kind of written these out is that notice that 5 pi over 12 here is the combination of 2 pi over 12 plus 3 pi over 12. Well, this means that I'm essentially finding sine of 2 pi over 12, which is pi over 6, plus 3 pi over 12, which is pi over 4. And so now I have my A and I have my B in terms of angles that are on the circle. So now is the point where I'm going to use the formula and use the identity. So the above identity is sine of angle A, which is pi over 6, cosine of angle B, which is pi over 4, plus cosine of angle A, which is pi over 6, times sine of angle B, which is pi over 4. So now I just need to go through and find these exact values. This is where your unit circle will come in handy. So hopefully you have one out. If not, I would pull one up because I'm just going to do these essentially from my head. Sine of pi over 6, that's the y coordinate at pi over 6. That would be 1/2. Cosine of pi over 4 is radical 2 over 2. Plus cosine of pi over 6 is radical 3 over 2. Sine is radical 2 over 2. Now notice when I go through and I'm saying sine of pi over 6, again, when I say 1/2, that's my answer. I'm not saying sine of 1/2, right? Sine of pi over 6 is the y coordinate there. So once I pick that y coordinate out, that's the answer to this entire first little expression. This entire expression is root 2 over 2. This entire expression is radical 3 over 2. This entire expression is radical 2 over 2. So be careful because I've always seen people that just want to keep dropping down the trig. But once you go to the unit circle and you say sine pi over 6 is 1/2, we're done with sine. It's time to move on to the next piece. And so the remaining step here is really just to kind of simplify. Now, I want to encourage this now because this is going to come up in a later example. Don't ever simplify early or like too soon. For example, always go ahead and multiply out the pairs of numbers here first. So like in this example, we're just going to multiply straight across. So 1 times radical 2 is just root 2. On the bottom, 2 times 2 is 4. Plus, when I multiply square roots, we multiply the insides together, so I get root 6 over 4. And the reason why I don't want to simplify is because notice, because I'm adding fractions, I need the same denominator, and I have that. If I was to simplify beforehand, I wouldn't have the same denominator, and I'd have to ultimately go backwards, and I'd have to undo what we did. And it's just taking extra steps, and more steps lead to more mistakes, etc. So as an encouragement, again, don't simplify until the very, very end if we even can. So here, I'm just going to write this as one single fraction, which is really just putting the numerators together all over that common denominator. This would be the exact value for sine of 5 pi over 12. So if you were to take your calculator, if your calculator is in radians, if you were to do sine of 5 pi over 12, you would get the decimal version of root 2 plus root 6 over 4. All right, and although this answer here doesn't look very, very pretty, mathematically speaking and theoretically speaking, this is the exact answer. Versus if we were to do this experimentally and I needed to actually know what this value was, we could only approximate it, meaning that my answer is wrong technically, right? It's off by however I round it. And so this represents the exact solution. There's no error here, which is really, really important in theory. All right, and so let's dig into now part B, so something that's a little bit larger in terms of a radian measure. So it also deals with cosine. So let's do cosine of 19 pi over 12. Again, like we did in part A, my goal here is to break 19 pi over 12 into two angles from the unit circle being added together, right? So that kind of combination. So that means I'm going to use pieces again from the original part here. I just need to make sure they add up to be 19 pi over 12. Now you'll notice that there is no pair here that would get me to 19 pi over 12. In other words, I need to use angles that are not in the first quadrant. I need to use multiples of these and trying to find some combination. Now, generally what I tend to do is I want to break this 19 pi over 12, or really just break 19 down into two even numbers or two odd numbers where 12 can be simplified down. So essentially, I want to break it down into something like 16 pi over 12 and 3 pi over 12. So notice that if I was to go through and add these numerators, I would get 19 pi over 12. So this is a pair that works. And it's a pair that I want to use because if I reduce or simplify each individual piece here, 16 pi over 12 is 4 pi over 3, which is on the circle. And then 3 pi over 12 is pi over 4, which is on the circle. And so the goal here is when I pick these two measurements, they need to simplify or reduce down to something on the unit circle. Because again, my goal is to find the exact value. And so that's kind of one approach, is to try and break it down into two numbers that can be simplified. Another approach is, again, to think about it in terms of multiples. Again, I know that I could take this angle right here, and if I take 4 of those, that would be worth 16, and adding 1 of those would get me to 19. And there's the two numbers that I used originally. You could also essentially say, I want 8 values of this and 1 values of this. So that would give me 16 plus 3, which is 19. So it's another way to go through and kind of solve the problem. It does not matter the combination as long as you're simplifying accurately and your combination adds to give you what the original problem is. So as long as you're choosing your numbers right, it doesn't matter. The answer will always be the same. All right, and so now I essentially have my A, I have my B, right? There's my A, there's my B. So I'm going to use the formula. So the formula tells me if I have cosine of A plus B, this is equal to cosine of A, so 4 pi over 3, times cosine of B, which is pi over 4, minus sine of A, which is 4 pi over 3, and sine of B, which is pi over 4. And now I'm going to go through and using a unit circle, I can find the exact values. Cosine, again, is the x-coordinate. So the x-coordinate at 4 pi over 3 is going to be negative 1/2. Cosine of pi over 4 is root 2 over 2, minus sine of 4 pi over 3, which is negative radical 3 over 2. It's the y-coordinate. And sine of pi over 4, which is positive root 2 over 2, the y-coordinate there. Next step is to simplify. Again, I'm just going to multiply throughout. So I have negative 1/2 times negative root 2 over 2. Well, that's negative root 2 over 4. Again, just multiplying straight across. Same thing over here, multiplying straight across. I would get negative root 6 over 4. But because it's minus overall, these two are just going to make one plus sign. So I'm just going to go ahead and change that and just go ahead and make it positive. And that's just because of the double negative. And so when I write this as a single fraction, you can write it as negative root 2 plus root 6 all over 4. I'm actually going to write it so it's saying root 6 minus root 2. It's just a little bit easier to put that minus in the middle and just looks a little bit better. And so this is what you would see in a textbook or if I was to work another problem, etc. That's how I would try and write it. All right, but there's using cosine and the angle sum identity. All right, so this leads us to the final one, which is using tangent. So you notice we're kind of walking through each identity, trying to get you used to how we use them. And so this would be tangent of 17 pi over 12. And so again, I need to find some kind of combination of the angles on the unit circle that when they add would give me 17 pi over 12. My technique again is I'm going to pick two numbers that'll add to give me 17, but can simplify with 12. So let's say, well, I know 3 works, so I could do 3 pi over 12. And so then this would have to be 14 pi over 12, which simplifies down into 3 pi over 12 would be pi over 4, so that one's good. 14 pi over 12, divide both of those by 2 would give me 7 pi over 6, which is also good. So this is good enough. Both of these work. And so then I'm just going to use the formula where A again is going to be pi over 4 and B will be 7 pi over 6. And I'm specifically going to look at my identity for tangent and I'm going to follow it. So that identity says tangent of angle A, which is pi over 4, plus tangent of B, which is 7 pi over 6, all over 1 minus tangent of A, which is pi over 4, times tangent of B, which is 7 pi over 6. All right, so now I need to go through and using the unit circle. This one kind of sucks again because remember that tangent of an angle is the y coordinate over the x. So again, I'm going to kind of do this in my head. I would encourage you to work this out on the side to kind of help double check. Tangent of pi over 4 is equal to 1. So that's the first thing in my numerator. Plus tangent of 7 pi over 6. Well, at 7 pi over 6, the y coordinate would be negative a half. The x coordinate would be a negative root 3 over 2. So this would come out to be essentially positive 1 over radical 3 once the 2 is simplified down. All right, then I would have 1 minus. Well, we already have our answers now, so tangent of pi over 4 is 1. Tangent of 7 pi over 6 would be 1 over radical 3. So this would give me 1 plus 1 over root 3 all over 1 minus 1 over root 3. So notice that they don't simplify, right? They're not the exact same. It's also kind of disgusting because I have a fraction here and a fraction here. And this I cannot have as a final answer because of how ugly it looks. So what I'm going to do is I'm going to multiply the top and bottom in this case by radical 3. Excuse me. And by choosing to multiply by radical 3, this is going to give me radical 3 plus 1 because these will cancel here as I distribute. And again, as I distribute, radical 3 minus 1 because these will cancel. And so this looks way nicer and way neater in terms of a final solution for us. And in the notes for this, the lesson plans for this, if you want to look at it, I actually choose to do different numbers here. And so the work actually comes out a little bit neater. And so it kind of shows you how different combinations can lead to somewhat easier work in the long run. I think, for example, I think I did 8 pi over 12 plus 9 pi over 12. And the numbers actually worked out a little bit nicer because it would be a combination of pi over 3. So the y coordinate would be the root. And so I wouldn't have this like 1 over radical thing. But this is a good way because it now shows you kind of both approaches as you go in. All right, and so this is for using angle sum identities. So there's also angle difference. So what if I want to subtract the angles on the inside? And you'll kind of notice, again, the comment here is that all we're doing is we're changing the operation in the middle here. So instead of a plus, we have a minus. So you would think, or at least intuition would imply that if I'm going to change the sign here, it's probably just going to change the signs everywhere in the original formulas. And that's actually true. So in other words, sine of A minus B actually looks the exact same, sine of A cosine of B, but it's minus instead of plus. So it's minus here, cosine of A, sine of B. And this is where my trick of saying that it's sine, so the sign stays the same. So it's a lot of S's there. Kind of plays a big role here. Cosine, same format. So cosine of A, cosine of B. but the sign will change. So this will be a plus here, sine of A, sine of B. And then for tangent, it would still be tangent of A, but this time minus tangent of B. And then this is all over 1 plus tangent of A, tangent of B. All right, so now when you're looking at the project, and if you're attempting to do the project, you will see this, and it'll again dig into where these formulas come from. They stem from the angle sum, and we kind of talked about the key idea, but mathematically there's more specific things to kind of show. But the project will explore that a little bit further. All right, so the second example we're going to look at is now you doing this angle difference problem. So find the exact value. So you'll notice the directions will be the same. So find the exact value for each of the following expressions. So sine of pi over 12, cosine of 19 pi over 12, that should look familiar, and then cosecant of pi over 12. In other words, can the reciprocals kind of come in here? And so let's start with sine pi over 12. And again, this time when I'm doing my combination, I want to make sure that I'm taking my A and I'm subtracting my B. In other words, the goal here is to do a difference. And so I need to choose two angles that when I subtract them would give me pi over 12. Well, one combination that this would work with is 3 pi over 12 minus 2 pi over 12, right? This would work. And if I simplify those fractions, this would give me pi over 4 minus pi over 6. So there's my exact values. There's my radians from the unit circle. And so now I'm just going to use the identity that I wrote up above to go through and solve. So this would be sine of A, and I'll kind of notate that. So this is A, this is B. So sine of A, so that's pi over 4, cosine of B, so pi over 6, minus cosine of A, pi over 4, so it kind of takes turns, and then sine of B, which is pi over 6. And then using the unit circle, we can find each of these exact values. Sine of pi over 4 is root 2 over 2. There's the first one. Cosine of pi over 6 is radical 3 over 2. And then minus cosine of pi over 4 is root 2 over 2. And sine of pi over 6 is 1/2. So you'll notice that it's the same numbers over and over again because there's only really 3 different numbers on the unit circle in terms of the coordinates. So hopefully this is kind of getting a little redundant in terms of this next step because I just want to simplify. So radical 2 times radical 3 is radical 6 over 4 minus radical 2 over 4. And so my final answer will be root 6 over root 2 all over 4. There's my exact value. Now, if you're doing these accurately, it's actually true that this should always be over 4, and then you'll have some kind of combination here of either radical 2, radical 6, or radical 3. Generally, that's always essentially what that'll boil down to. So you'll know kind of if you're on the right track or not. All right, so there's sine of pi over 12 and finding its exact value. Now, cosine of 19 pi over 12. Again, we did this one earlier, but let's look at this one and see if we can do it in terms of angle difference. So instead of adding two angles to give me 19 pi over 12, is it possible to come up with a combination where I could subtract? Again, I know 3 pi over 12 is an angle that works, so I could do 22 pi over 12 minus 3 pi over 12. So I know that this combination is good because that'll give me 19, and it's also helpful because 22 can be simplified with 12. So let's go through and try this approach. All right, so I'm going to follow the formula. So the formula, or actually, hold on, let me simplify this just to prove it. So 22 pi over 12 is 11 pi over 6, so that's on the circle, so that's nice. And then 3 pi over 12 is pi over 4. And we've seen that one a couple times now. All right, so now I'm going to use the formula where this is my A, this is my B. And so now I'm just going to follow the identity. So identity says cosine of A, so 11 pi over 6, cosine of B, which is pi over 4. The operation changes, so it's plus sine of A, angle A, that's a tongue twister, and then sine of angle B, which is pi over 4. And so now I can use the unit circle to evaluate, so cosine of 11 pi over 6, this would be positive radical 3 over 2. Cosine of pi over 4 is giving me radical 2 over 2, plus sine of 11 pi over 6 is going to be negative 1/2. And then sine of pi over 4 is radical 2 over 2. So now I just need to simplify, and so this gives me radical 6 over 4 minus radical 2 over 4. And so I get radical 6 minus radical 2 over 4. And that's my final. And I was just kind of double checking in my head real fast. And this is really, really important because this answer here, this radical 6 minus radical 2 over 4, notice it is the same here, and that's what was kind of freaking me out at first. But it just shows you that those two answers they just have the same exact value. Really what I wanted to point out was if we go back up to the first example, that's the answer we got here. Whoops, I erased it. There's my pencil. Right, which matches. And that's really important because we were looking at evaluating the same cosine. And so it's really kind of neat to show you that that comes out. And so the thing that we can take away then, and that I want you to take away from this example, is that it does not matter whether you do subtraction or whether you do addition. So angle sum versus angle difference, you can approach a problem either way, right? So what I'm going to give you in terms of directions, or if you're writing your own question, is it's just going to say find the exact value using angle sum and angle difference, or just find the exact value, right? And so as you go through, it's just up to you to decide how you see the combination. Is it better for subtraction, like with pi over 12? I thought I had my highlighter. Or addition with 19 pi over 12, because subtraction uses larger values, so it can be kind of tricky. All right, so let's look at cosecant of pi over 12. I chose this one really just to kind of help show what we do with cosecant. If you recall, cosecant is the reciprocal of sine, right? So if I was to flip sine over like so, this is saying the equivalent thing. And sine of pi over 12, I would then go through and try to do this as a combination, right? I would say, okay, well, do I want to do sum or difference? And remember, if you remember, sine of pi over 12 should look really, really familiar. It's the first example here. And we could break this down into 3 pi over 12 minus 2 pi over 12 and work this out. But we've already got the answer. So I'm really just going to go through and take our answer from A, which was sine of pi over 12 was root 6 minus root 2 all over 4. And because this is in the denominator, remember it's keep, change, flip. That's almost KFC. And so this would come out to be 1 times the reciprocal of the denominator. So that would just be 4 over radical 6 minus radical 2. Now, you could leave this as your final. Generally speaking, we don't leave radicals in the denominator, even if they're being subtracted like this. And so I would want to rationalize. And so if you remember from when we did doing the coordinates and doing trig values or trig ratios with the exact value stuff, is that when you want to do a conjugate, you're choosing the terms to be the exact same, but you change the sign in the middle. So I would be multiplying top and bottom here by radical 6 plus radical 2. And by choosing to multiply by this, it's going to get rid of the pieces on the bottom. And the way that it gets rid of those pieces, so the top is just going to be the 2 multiplied together like that, just kind of slide them. On the bottom, because of this, it's a difference of squares type problem. So when you multiply it out and you FOIL this out, since it's a binomial times a binomial, I only really need to do the first terms and the last terms, meaning I'm doing root 6 times root 6. Well, that would be square root of 36, or just 6, right? The square roots cancel, minus radical 2 times radical 2, which is just 2. And so I would see that this would be 6 minus 2, which is 4. So the 4's cancel, and the exact answer is now just root 6 plus root 2, which is way neater than looking at it the way that we had it beforehand. So be prepared for if you want to take this to the next level with these reciprocals. You don't see it very often, but this is what you would have to do. You do the reciprocal and you just solve it still based off of sine, cosine, or tangent. So there really is no angle sum formulas for cosecant, right? There's really no angle difference formulas for secant because it's all just based off of the big 3, since cosecant, secant, and cotangent are just the flips and kind of built-in reciprocals for that. So That's very, very nice. All right, now the next thing I want to do, example 3, is look at another kind of application here. This is going to set up kind of another identity and really kind of establish kind of an interesting piece of the unit circle that we have talked about, but this kind of gives you a way to see it algebraically, and kind of working through it in terms of these identities that we have so far. So use the angle sum and difference identities to rewrite each trigonometric expression below. Write each answer as an identity, so we're going to write it as an equation, and then check it for theta is equal to pi over 3. So in this problem here, theta is just any angle that you want it to be. But notice in A, we're doing cosine of pi specifically minus theta. Now this is the difference, the angle difference for cosine. So I'm just going to use the formula for that. So that says cosine of A, which is pi. That's my first piece here. Theta is going to be B. So then the next piece would be cosine of theta. Then because it's subtraction, this would now be plus sine of A, which is pi, sine of B, which is theta. And so here's my angle difference formula written out. Now, I can't really do anything with this cosine theta or this sine theta, so this stuff is just going to drop down. So I'm going to say equals to, well, this is just cosine theta, right? It depends on what theta is, and that's just sine theta. Again, depends on what theta is. It's this part here, cosine of pi and sine of pi, that we can actually evaluate by going to the circle, since I have that angle given to me in terms of pi. So if I go to pi, cosine of that would be -1. Sine of pi is actually 0. So this entire second term here is just 0. It's gone. So the entire problem boils down to then just negative cosine of my angle, whatever that may be. And so with my left-hand side here, dropping this down, I have this identity that says cosine of pi minus theta, so pi minus any angle, it's always going to be equal to negative cosine of that angle. So let's use pi over 3 to check this, and then we'll kind of talk about why this makes sense, and hopefully make the connection back to trig ratios in the unit circle. Theta was pi over 3, so I'm just going to do the left-hand side first. So cosine of pi minus pi over 3. Well, pi minus pi over 3 would be cosine of 2 pi over 3. It's like saying you have one whole item, and I want to subtract off a third. So that leaves me with 2/3. And so going to the unit circle, cosine of 2 pi over 3 would give me -1/2. All right, so then if I go to the right-hand side, I'm going to do negative cosine of theta, which is negative cosine of pi over 3. And if I do cosine of pi over 3, that answer is +1/2. But because I have the negative out here, it's negative overall. And notice that these match, which means the identity is true. All right, and now let's talk about it in terms of looking at this and why this makes sense. So if I have pi minus theta, think about where this would lie. Specifically, if theta is in, let's just say, the first quadrant. So if theta was something less than 90. Well, if I do pi minus that, then what you're essentially doing is you're finding an angle that puts you in the second quadrant, right? You're saying, okay, well, whatever theta is, let's take that from pi, meaning that this is theta. Well, this triangle right here, remember, is going to be the exact same mirror image of one if I was to put it in the first quadrant. So something like this. But the only difference is, although these y coordinates are the same, what's true about their x's? This one has to be negative, right? And this is true no matter where you are. And so this is the relationship between angles in the second quadrant and their reference given in the first quadrant. Remember, for cosine, the x values are negative because we're in the second quadrant. So for pi over 3, if you go to 2 pi over 3, they have the exact same x coordinates, except 2 pi over 3 is negative. So we need to negate our answer from pi over 3 so that it would balance and now it would work. All right, so that's the identity. That's what this first part is essentially describing as an equation. It's just that reference angle relationship there. And so let's look at, for B, sine of theta plus pi. And we can look at this in the same kind of sense, right? This is saying if you take an angle and I add pi to it, you're adding 180 degrees. You're flipping from the bottom half of the graph to the top half of the graph of the unit circle. And think about what that means then in terms of your sine values, which are your y coordinates. And let's see if the answer here makes sense. All right, so I'm going to use the identity again for angle sum this time, where that's my A and that's my B. And so the angle sum says do sine of A, so sine of theta, cosine of B, plus cosine of A, sine of B, which is pi. So we're going to see some very, very similar things like we did beforehand. Sine of theta is just that, so I'm just going to drop it down. There's nothing to do really with that. Cosine of pi was -1, plus cosine theta will just drop down. A terrible looking arrow. And sine of pi is 0. So, right, so the entire second term is gone again. And so I get negative sine theta is equal to sine of theta plus pi, which again should make sense when we think about it, because if you are in the top half of the circle, if you're up here, if I add pi to this, I'm going 180 degrees. Well, that means what's the difference between these two y coordinates? Well, this one would be positive and this one would be negative. But other than that, that's it, right? The values themselves should be the same. And so that's what this is saying. Whatever you get from this sine value, this y coordinate, it would be the same as that initial angle, just negated, because it depends on where you're at. If you're starting in the negatives, your answer is going to be positive, so negative and a negative. If you're starting in the positives, your answer is now going to be negative, so therefore it's negated. All right, and to show this, let's let theta be pi over 3, and let's just show that this works and that this is an identity. All right, and so I'm just going to do the left-hand side first, like we did in part A. So let's do pi over 3 plus pi. Well, if I add a whole unit to pi over 3, this means I'm going to have 1 1/3, or 4 pi over 3. And sine of 4 pi over 3 is negative root 3 over 2. All right, well, let's check now negative sine of just pi over 3. Well, sine of pi over 3 is radical 3 over 2, but again, I'm negating it according to that right-hand side. And notice again that these would match. So we're good. This is true. All right, so hopefully the visual kind of makes sense here. If not, hopefully the work does in and of itself. And if you want to check this with a different angle, you can. Choose pi over 4, choose 5 pi over 4, and go through and evaluate it and see if the two things hold true or not. All right, so there's one more example to look at. This is kind of the prime, like level 3 type of problem. Generally, if I'm going to give you an assessment, I'm definitely going to ask you this type of question. So make sure if you'll see this on the practice problems, take a look at it. If you have any questions, ask me and we can look at it during the virtual classes. But for sure, you will get this one from me, and you need to show me that you understand the basics of it to at least get up to a 100 for the formula specifically. All right, and so here's what example 4 says. Suppose alpha, all right, so this is just the lowercase for alpha, is in quadrant 2 and beta is in quadrant 3. So alpha and beta are angles, all right, and we know exactly where they're located from the standard position if I was to rotate, such that sine of alpha is 4 over 5 and cosine of beta is negative 3 over 4. So I know something about the trig ratios, or at least one of the trig ratios for each alpha and beta. So here comes the actual question. So find the exact value of sine of alpha minus beta and then cosine of alpha plus beta. So in other words, I want to go through and do the angle difference and the angle sum for sine and cosine respectively to this problem. All right, and so what I want to do is really just kind of start off and say, okay, if I have sine of alpha minus beta, let's write out what this is actually trying to get me to solve for. All right, and really all I'm going to do is go through and write out what the identity says, with A being alpha and B being beta. So this would be sine of alpha cosine of beta minus cosine of alpha and sine of beta. And I write this out more importantly to kind of show you that I know what sine of alpha is, right? That's given. I know what cosine of beta is, that's given. But I do not know cosine of alpha and I do not know sine of beta. right? I don't know what these values are. I need to find these if I'm going to go through and find the exact value for sine of alpha minus beta specifically. Now, when we go through and find these, notice I just care about what is the ratios. I do not care about what the actual angles are. So that's another big misconception that I want to be clear on. I do not need to find the angle for alpha. I do not need to find the angle for beta. All I'm going to do is start by sketching the angles. Like, where would they essentially be? So for alpha, I know that this angle is in the second quadrant. So if I draw my quadrants, I'm going to use blue for alpha. I know that this would put me somewhere over here in the second quadrant, right? That would be alpha. I know that for beta, I'm told that beta is in the third quadrant. I'll use red for beta. So I'm just going to draw an arbitrary line, and here is beta. Now, the following step is to remember that I can draw and represent these angles using reference triangles, and that the sine and cosine of these angles is the same as the sine and cosine of these reference triangles. So I'm actually going to take this triangle here and create it by drawing it to the x-axis. And so now I have this right triangle, which I'm going to try to over-exaggerate here. For the red, I'll do the same thing, and again, sketch it going to the x-axis. So now I have my reference. And I was told that for alpha, sine of alpha was equal to 4/5, meaning I know the opposite and hypotenuse for this triangle. This would be 4, this would be 5. All right, I was also told that for beta, cosine was negative 3/4. And notice this should make sense because if that's my adjacent, that's my hypotenuse, because I'm moving to the left, that should be -3, and the hypotenuse is always positive because it's a distance from the origin, or radius of a circle if you want to think about it like that too. So notice if I'm trying to find cosine of alpha and sine of beta, this means I need to figure out what these missing sides are. What's the x-coordinate here, and what's the y-coordinate here? Well, they're triangles, so we can use Pythagorean. All right, so I know that x squared plus 4 squared is equal to 5 squared. So x squared plus 16 is equal to 25. X squared is equal to 9. So I get x is equal to, plus or minus 3. Now I know that I need to choose -3. The reason, look at what quadrant I'm in, right? Because I'm in the second quadrant, x has to be negative. All right, well, what about over here for beta? All right, so I know over here that I have -3 squared plus y squared has to be equal to 4 squared. Now be careful here because although the other one for alpha was a Pythagorean triplet, like a 3, 4, 5, this is not, because the hypotenuse is not 5. All right, so be careful here. We actually need to solve this one out. All right, so -3 squared is +9. Be careful with your calculator. Plus y squared is equal to 16. Subtract, so y squared is equal to 7. And then the square root gives me a plus and minus, but I know I need this to be negative because I'm in quadrant 3 and I'm going down, right? The y-coordinate is negative. And so I can now go into my formula for sine of alpha minus beta, which again was sine of alpha cosine of beta minus cosine of alpha sine of beta. And I can now fill in based off of the two triangles that we've got, my references, right? I know that sine of alpha was 4/5 because that was given. Cosine of beta was -3/4 because that was given. And what I needed to know, I can now find. Cosine of alpha, well, that's looking at my blue triangle, adjacent over hypotenuse, so -3/5. Sine of beta is opposite over hypotenuse for my red triangle, so that would be -√7/4. This is the example that I was talking about where you are going to be tempted to cancel out this 4 and this 4. Do not do that. The reason being is we want to maintain these two pieces on the bottom because they match no matter what. And remember, we're going to make this one unified fraction, so I need the denominators to always match. So in the first piece, 4 over 5 times negative 3 over 4, just going to go straight across. So negative 12 over 20. Again, you're going to be tempted to simplify. Please do not do that. Minus, and the second one, 3 root 7 over 20. And the reason I don't want to simplify is because I'm making this into one single fraction. And I can't reduce the second fraction, so I'm not going to reduce everything. This is it. This is my exact value for sine of alpha minus beta. There's a lot of steps here, and this is why this makes it a level 3 type problem, because it really is a full rounded problem, because it shows you and shows me that you not only know how to do the identity, but you also understand reference triangles and unit circle and how to work those pieces. All right, now what's really nice is for B, we actually have all the pieces. We just need to use the formula. So we have cosine. I was supposed to find cosine of alpha plus beta here. So using the identity, this would be cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. And again, we found these ratios. I just need to now plug and chug, right? Cosine of alpha was, negative 3 over 5. I'm trying to remember without looking up. Cosine of beta was negative 3 over 4. That's what makes it so tricky. Minus sine of alpha, which was given to us, that was 4/5, and then sine of beta, which was negative root 7 over 4, what we had to find. And so now I'm just going to multiply these two things out. So negative 3 and negative 3 is 9 over 20. This will turn out to be plus 4 root 7 over 20. That's the double negative here. And making this into one single fraction, I get my final. All right, so in conclusion, all right, so to kind of end this video out, this is not, I'm not going to put this on the formula sheet just because sometimes it can be a little confusing, but I'm going to put it here in case you Google it, Google stuff or whatever. They generally write the angle sum and angle difference as a combined identity. So if I was to do sine of A plus or minus B, this would be sine of A cosine of B plus or minus cosine of A sine of B. In other words, the top sign, if you have plus, goes with the top sign here. Bottom sign with bottom sign. Cosine of A plus or minus B is cosine of A cosine of B. Here, the signs swap, minus plus. Sine of A sine of B. And that's because, again, remember, the signs change. So if I have plus on the inside, I'm subtracting on the outside. For tangent, we have this as well, where this would be tangent of A plus or minus, because that always matched, tangent of B. But in the denominator, it changed. 1 minus plus tangent of A, tangent of B. All right, so this kind of builds onto our identities that we have. We'll continue to use these, and we'll use these in the next video. Again, if you would like to do this as an assessment, make sure to look at that assessment doc, so that way you're not completely lost. And if you have any questions about the directions or anything like that, please let me know. And I'd be more than happy to give you a push in the right direction and try to help clarify some things if needed. Otherwise, make sure you take a look at the practice. If you're writing your own assessment, use the practice problems as examples to help you find the, really rewrite and have some really good questions that I can go through and then you can correct me on. So thank you for watching, and I look forward to hearing from you if you have any questions or anything like that. And until the next time I see you again.